Welcome to today's Explainer. We're jumping into a topic today that honestly trips up a lot of people. But right here, right now, we are completely removing that math intimidation factor. Welcome to Cracking Integers, the ultimate playbook. I want you to think of math not as some dry, dusty subject, but as a game. And to win absolutely any game, you just need to understand the rules. So today, we're doing a super easy step-by-step decode of the integer rulebook straight from our source material. Grab your mental controller, get focused, and let's get ready to play. Okay, let's just dive right into this with a question you probably weren't expecting. Have you ever actually thought about how lost goats essentially invented math? Seriously, think about it. Early humans had a very real, practical problem. Their goats kept wandering off. To keep track of their livestock, they simply started counting. One goat, two goats, three goats. It was literally the most natural thing in the world to do. And because it was so intuitive, the very first numbers ever created were aptly named natural numbers. But as you'll see, the game was just beginning. All right, level 1, the origin story of numbers. So we're going to see exactly how humanity went from just counting livestock in a field to building these incredibly complex, structured mathematical sets. Following the timeline of human history, as we just established, in ancient times we had natural numbers for counting: 1, 2, 3, 4. But what happens when you have 0 goats? Someone, probably very frustrated, needed a way to represent literally nothing. Enter the brilliant mathematicians from classical India, Aryabhatta and Brahmagupta. They collaborated and invented 0. When you add 0 to the natural numbers, you suddenly have a complete set, which mathematicians called whole numbers. But humanity being humanity, we kept complicating things. People started owing things to each other, creating deficits. Well, how do you represent a lack of something or less than 0? That is when we added negative numbers to the mix, officially giving birth to the robust set of numbers we call integers. Let's really establish a crucial definition here, because this is where people often get tripped up. An integer is a complete, solid number. Think of it kind of like organizing a crowded bookshelf. You don't want half-torn books mixed in with full books, right? It makes a mess. So mathematicians decided to keep integers strictly separate from fractions. Integers are whole items. There's no 1.5, there's no 1.3 or 1.6, no fractions, absolutely no decimals allowed, just pure, complete numbers, stretching from negative infinity all the way to positive infinity. And this brilliantly illustrates what holds that whole infinite system together. I absolutely love this quote from our source. 0 is the referee. Just a fantastic personification. Picture 0 standing right in the middle of the number line with a whistle. It points to the right and tells the positive numbers, hey, you guys head that way toward positive infinity. It points to the left and tells the negatives, you go that way to negative infinity. 0 itself, it's not positive, it's not negative, it's just the ultimate, unmoving, neutral referee right in the center of the whole shebang. Now, I kind of want to test your mathematical instincts for a second. Picture the number negative 1,000. I want you to imagine this massive number sitting way, way down on the negative side of the number line. It looks incredibly big, right? But what is its actual value in the game of integers?
Well, here is the mind-bending rule of the negative world. On the left side, we have negative 1,000. On the right side, we have negative 3. Now, in the positive world, 1,000 absolutely crushes 3. But a negative sign indicates a deficit, a lack of something. If you are lacking 1,000 things, you are in a much worse, much lower position than if you are lacking just 3 things, because numbers on the number line always increase in value as they move up and to the right. Negative 3 is actually much, much bigger than negative 1,000. So, the crucial point is, in the negative zone, the bigger the number looks, the smaller its actual value is.
Moving on to level 2, multiplication and its moods. Master the number line? Awesome. Now it's time to level up. Let's see how these integers behave when they start interacting and multiplying with each other. The source material uses a really fun metaphor here about human nature to explain this. Think about people hanging out together. If 2 incredibly positive people get together, the vibe is great. It's a happy, positive result. But surprisingly, if 2 highly negative people get together, say they both just want to complain about the world and burn it down, they actually agree with each other. Their identical mindsets create harmony, so a negative times a negative equals a happy, positive result. On the flip side, if a super positive person hangs out with a deeply negative person, their mindsets clash. It totally brings the mood down. Different signs always lead to a sad, negative result. So the rule is simple. Same signs, happy, positive answer. Different signs, sad, negative answer.
Now, what's really interesting about this is how incredibly cooperative multiplication is as a function. I mean, it's the ultimate rule follower. Just look at these properties. Closure? Yep. An integer times an integer is always an integer. 4 times 3 is 12, perfectly enclosed. Commutative? That just means you can swap the order. 3 times 4 is exactly the same as 4 times 3. Holds up perfectly. Associative? Group the numbers however you want, the final answer isn't going to change. Distributive? A number outside the bracket perfectly distributes to the numbers inside. It also has a multiplicative identity, which is really just the number 1, because any integer multiplied by 1 stays exactly the same. Multiplication just plays so nicely.
Which brings us to level 3, division, the rule breaker.
Because every game has a tricky character, right? If multiplication was the perfectly behaved sibling, division is a one flipping the game board over and refusing to cooperate. There is a stark contrast between these two operations. We just saw multiplication gracefully hold up all these mathematical properties, but division? It literally shatters them. Let's look at closure. 6 divided by 2 is 3, an integer. Great. But 3 divided by 2? Well, that's not a whole number anymore. It's an incomplete number, so closure fails. How about commutative, swapping the order? Well, 6 divided by 2 is 3, but 2 divided by 6 is 1/3. They are absolutely not equal. Fails again. Associative, fails. Distributive, fails. The rules of multiplication simply do not apply to division. It's a completely different beast you have to watch out for. But hey, before we leave division entirely, I gotta give you a crucial cheat code straight from the source. Listen closely to this convention. Denominators absolutely hate negativity. If you're doing a division problem and you end up with a negative sign on the bottom, for example, a 3 over a -2, you never leave it there. It's standard mathematical practice to always shift that minus sign to the top. So 3 divided by -2 officially becomes -3 divided by 2. Keep that cheat code in your back pocket for sure. It will save you on exams. All right, level 4, the boss fight, cracking brackets. Okay, we've powered through the levels. You have your weapons, you know the integer rules, and you've got the cheat codes. When you see a massive math problem with a terrifying number of different brackets, here is how you systematically conquer it. The crucial point is establishing absolute priority. You cannot attack a boss fight randomly. You need a strict, disciplined order of operations. Step 1 is the vinculum. It's that little flat line drawn over top of certain numbers. The source, hilariously but accurately, calls this the BOP, or the father of all brackets. Whatever is directly under the vinculum gets solved first, no questions asked. Once the father is cleared, you move to step 2, the standard small brackets, the parentheses. Then, step 3, the curly brackets. And finally, step 4, the heavy-duty big brackets. Memorize this sequence and absolutely no complex equation can stop you. Let's actually put this to the test and execute a combo move. Take this absolute monster of an equation. 30 minus big bracket 26 minus curly bracket 15 plus small bracket 8 minus vinculum 6 minus 3. Okay, deep breath. Let's attack. First we hit the vinculum. 6 minus 3 equals 3. Boom, the father bracket is cleared. Now we look inside the small brackets. We have 8 minus the 3 we just solved for. That equals 5. Small brackets cleared. Moving out to the curly brackets. 15 plus the 5 we just generated gives us 20. Curly brackets gone. Now for the big brackets. 26 minus 20 equals 6. Big brackets destroyed. And our final strike to win the whole game, the 30 waiting patiently on the outside, minus the 6 we just resolved. 30 minus 6 is 24. Boss defeated, flawlessly. And there you have it. You've successfully navigated the entire playbook of integers, from counting ancient goats to establishing the zero referee, all the way to flawlessly executing the bracket hierarchy. You now understand the mechanics running behind the numbers. As our enthusiastic source says, mastering this is really all about creating a bowal, a massive positive disruption. Now that you have the ultimate cheat codes and clearly see how this game is played, it kind of makes you wonder, what other incredibly complex systems in our daily lives are secretly being run by just a few simple, unbreakable rules? Thank you so much for joining me on this explainer today. Stay focused and keep learning.